Okay, so let's go step by step here through one of these null hypothesis problems. Pause the video if you need to read the actual question. Essentially what we have is blood pressure in males. We want to know if administrators, so male administrators, have a different average blood pressure than just typical males in that group. So the first thing we set up is our null and alternative hypothesis. The null hypothesis for everything we've done so far should be mean equals. So it should always have a mean equals. Whether it's one tail or two tail, we should always have this mean equals something, because that lets us draw our normal distribution. If we have an equals, then we can actually set a mean for this normal distribution. Otherwise, we don't really know where this normal distribution is located at all. So that's the important part of the null hypothesis, to make it a mean equals something. And what does it equal? Well, it equals the population mean, whatever we're looking at here. So in this case, it would be the 128 is the population mean. Notice that there's two means. There's this mean right here, and then we also have this mean of 132. So how do we know whether to do a 128 or the 132? Well, for one, this is a sample mean. So a sample mean would be x bar. The null hypothesis should always be a population mean. It should always be mu. That would be one way that you could think of it. Then the alternative hypothesis, here's where we have to look at the question we're asking. So it says, do they have a different average blood pressure? Different could be higher or lower. We're not necessarily specifying. So we just put not equals to. So your alternative hypothesis should never have an equal sign in it, right? The null hypothesis should definitely have an equal sign. Your alternative hypothesis should not have an equal sign. It should either be not equal to, or it could be less than, or it could be greater than, but it definitely should not have an equals in it. And this number should be the same, just so that if we end up rejecting this, then we have whatever is left over from rejecting that. So that's the null hypothesis. At this point, you could go ahead and set up your normal distribution. We could even put our standard error in there. So remember, this is the distribution of sample means. This is not the distribution of males' blood pressure, of individual male blood pressure. This is the distribution of means of sample size 40. That's what we're looking at here. The whole problem is based around that. And so to get this standard error, we would take the population standard deviation, which is 10, and divide by square root of the sample size, and that'll give us 1.58. So that tells us how big the standard error is here. So right away, we know that if we go one of these out to the left and one to the right, that'd be 126.5 to 129.5. We would have 68% of the sample means would be within that range. So what we want to know is our sample mean of 132, where does that fall in the big picture here of all these infinite numbers of sample means? Where does that 132? We know it's higher than 128, so it'll be up here, but we need to know how far out it is, and that's what we do next. So we calculate a z-score. The z-score for our sample mean, we subtract it from the mean of all the sample means, which is that 128, and then divide by standard error. Why don't we just divide by the standard deviation of 10? Why do we divide by this entire thing? Well, if we were just looking at how a single male compares to all these other males, then we would just divide by 10. We would just divide by the standard deviation. But what we're working with here is an entire sample, and that's why we need to divide by the sample error, not just the population standard deviation. So we set that up, we end up getting a 2.53 over here, which says that we're 2.5 standard errors above the mean, so we're somewhere up here now. And right away we could know that that's going to be pretty unlikely. 2.5 is pretty high above, but we should see this calculation through. So how do we actually get this p-value? Once we get the z-value, how do we get the p? Well, we look up this z on the chart, 2.53 on the chart. Remember, this is a z-value, a z-score. So we're looking in that table A, we're looking on the, actually, oh, I don't have it scanned in. So it would be looking for 2.5 on the left and then going over to the 0.03, and that would give us our value of 0.9943. So how does that help us? Well, the number in that chart always gives us the area to the left of what our z-score is. So our z-score was right here. It's right there, 2.53, and it tells us that 99.43% of the sample means will be less than what ours was. But what we're working with here is a tail test, right? We have a two-tailed test in particular, which means we're interested in the tail of the normal distribution. Not this thing here is called the body. The bigger part is always called the body. The smaller part is called the tail. And so we're interested in the tail. So we don't want this big 99.43%. We want the little leftover part. We want 1 minus that 0.9943. But we don't just want that tail, because remember all the way back to our alternative hypothesis, we had a two-tailed test. It was not equal to 128, which means it could be less than, could be greater than. So here's the greater than part, here's the less than part. How do we know how much area is down here on the left side in the tail? Well, it's going to be the same as whatever's here on the right side because it's a symmetric distribution. So whatever that is, 0.0057, if you work it out with the calculator, you multiply that by 2 in order to get the p-value. And then that gives you the p-value of 0.011. Going all the way back to the beginning, if this had been a one-tailed test, so mean is greater than 128, when we get that p-value over here, or that value over here in the tail, we would not multiply that by 2. If this was a one-tailed test, we only want one of the tails in our result, not both of them. But in this case, we did have a two-tailed test, so 2 times this amount gives us 0.011. Now we compare it to whatever our cutoff was to see if we're extreme enough to reject the null. And indeed, it's less than 0.05. Again, that saying is p is low, the null must go. So here was our null. This is the thing that must go. This is the thing we must reject. We must reject the idea that these male administrators had the same mean as the males in general in that age group. So if we reject that, what are we left with? We're rejecting the thought that these administrators have the same blood pressure as normal males. What does that leave us with? That leaves us with the alternative hypothesis, that male administrators do not have the same mean as the males in their age group. So the way we write that in plain English, the sample does provide evidence that male administrators have a significantly different blood pressure than males in general between the ages of 35 to 44. Notice that we could say significantly higher. Even though our original alternative hypothesis, we didn't know which way it would go, in the end, we did end up going higher. So it's legitimate to say higher. It's okay to say just a significantly different blood pressure, or in your conclusion here, even though it was a two-tailed test, because your sample really was significantly higher than the mean, it is okay to say that the male administrators have a significantly higher blood pressure than males in general.